Hey everyone, welcome back to AP Precalc. This is lesson 2.8. Let's get right into it. All right, so here's a bell ringer for today. Pause the video if you haven't done it yet because I am about to go over the answer. The table gives the values of function f for selected values of f. The function g is given by this equation, 9 to the power of x minus 8x. What is the value of g of f of 1? And so what we want to do here is this is a composite function. With these, you want to work from the inside out. So the first thing we want to just find is what is f of 1? And that we're going to look at this function. And so f of x, when x is 1, means f of 1 should be equal to 1/2. So now we just want to find g of 1/2. So all we got to do here is just plug 1/2 into this function. So this is 9 to the power of 1/2 minus 8 times 1/2. Remember, anything to the power of 1/2 is the square root of 9 minus, and then 8 times 1/2 is 4. This is 3 minus 4, which is -1, and that should be our answer. So A is the correct answer there. So today we're going to be looking at inverse functions, and this is a really important lesson because we will be looking at inverse functions for every different type of function we study in this course. Not just polynomial functions, but exponential, logarithmic, trigonometric, every single type that you can think of, we will look at its original and its inverse as well. So an inverse function or inverse relation will basically undo a given relation. It's like the same thing as Control Z on the keyboard. And so every inverse relation can be found by switching the x and the y values. For example, if we have the point 2 comma 5 on a function, on the inverse, the point 5 comma 2 will be a part of the inverse. So we're going to look at inverse functions numerically today, analytically, and then graphically, so with tables, equations, and then graphs as well today. So let's start pretty easy with tables. To find the inverse of a table, you just need to swap your x and your y values. So find the inverse relation of the given table. Here we're going to move all our y's into our x's and then move all of our x's into our y's. So here, moving our y's, we have -1, 2, 0, and 2. And then for our x's, moving them to the y's for the inverse, this should be 1, 3, 4, and 6. So that's our inverse table there. If we take a look, the original table is a function because each x value has exactly one y value, right? So we see every single x has exactly one y. There's not like there's multiple x's that or the same x that maps to different y values. However, the inverse, right, this table right here is not a function because the x value of 2 has two different outputs. Let me not write the number. Let me write of 3 and 6, right? So if you take a look, the number 2 here is seen twice, and it maps to two different outputs. What that looks like is if we graph that, right? Here, let's say this is 2, 3, and 6. 2, 3, and 2, 6 would both be a part of that. And as we know, to determine if something graphically is a function, we would do the vertical line test, which it would break the vertical line test. So the inverse is not a function, the original is a function, and then this is not a function here. Because we can switch the x and the y values, we know if AB is a point on a table, then B comma A will be a coordinate pair on the inverse function, and that will be really important for us with the next few problems. And so example number 2, let f of x be a continuous function with selected values in the table below. Find the values if possible. So some of these may not be possible. So let's start with A. Here, f of 5, this is not doing anything with inverses. This is just reading a table, right? F of x. when x equals 5 is negative 8. Now we have a composite function. This is from last class, so f of 4. Here, let's just find f of 4 first. This is negative 9. So now this just becomes negative 9. And then f of negative 9 should be negative 7. So that should be our answer for part B. And then part C, we have the inverse of negative 9. So you know how for part A, we looked for x equals 5 and then read our corresponding y value, or f of 5 value, which was negative 8. When you have the inverse, you're going to go the opposite direction. Here we're seeing where is f of x equal to negative 9, and then looking for a corresponding x value. So just think about it as you're going from bottom to the top when you're dealing with inverses, and top to bottom when you're reading a regular table. So this should be positive 4 here. All right, let's try example 3. Pause the video now and try to work through this yourself, because I'm about to go over the answer. Here, f of 2, we're just reading it like this, and so that should be 10. The inverse of negative 3, we now look for negative 3 here. You should get 7. F of 10, just reading it from here going down, this should be 8. F of 7, so if I erase what we have here, for f of 7, you just look at 7 here and then go down to negative 3. Inverse of 7, you're looking for 7 here and going up to negative 1. And then the inverse of 2, you look for 2 in your y's and then go up to negative 3 there. So that should be your answer for example 3. Example 4, we have one more of these tables to work with. Here we have a composite f of 0. This should be f of 0 is 1, so this is really just f of 1, which from the table is negative 1. Now we see g of negative 3, and so this is another way that AP could ask this question of like inverses, is they will say let g, a new function, right, because this is the graph of f. Let g be the inverse of f such that g of x is equivalent to the inverse of x, or the inverse of f. And so when we say g of negative 3, another way to write that is f prime, or f inverse, sorry, of negative 3, there. This, you're just looking at it here and then going up, so this should be positive 4. So 4 should be our answer there. So just think of g as like f, or the inverse of f. G of 6, you're looking at 6 here and going up to negative 3. G of 1, here you're looking at your inverse here. You should get 1, so now it's just g of negative 1 just becomes 1 on the inside there. And then 1 looking up that way should be 0, so that should be our answer there. This is now the inverse and then the original of negative 2. F of negative 2 should just be 3. And now the inverse of 3 should be, and what do you know? It actually goes right back to negative 2. So negative 2 should be our answer there. And then this is just another way of saying just the inverse of negative 3. So you're going up to 4 there. All right, so that's example 4. Example number 5. Find the inverse for the equation f of x equals 3x minus 1. All right, so the way to find inverses with equations is pretty simple. What you want to do is first replace f of x with y, right? If I write f of x equals 2x, this is the same thing as like y equals 2x. So here we'll write y equals 3x minus 1. And then what we want to do is switch x and y. So x equals 3y minus 1. And then to find the inverse, solve for y. So here we're going to add 1 to both sides to get x plus 1 equals 3y, and then divide both sides by 3 to get x plus 1 over 3 equals y. And then I'm going to switch just the sides of the equation just to keep it nice. And then we want to swap y back out with, this time we found the inverse, so we'll write it like the inverse of f equals x plus 1 all over 3. And so the inverse function of f of x is written as f inverse x there. All right, so this should be our answer to example 1, and we will need to use that again later. All right, so example 6, here we got 4 equations. Try to find the inverse function for each of the following. So I'm about to do it now. So this should be just swapping out f of x with y. Y equals negative x plus 3. Then you want to switch x and y. So x equals negative y plus 3. And then solve. So x minus 3 equals negative y, subtracting 3 from both sides. And then I'm going to multiply both sides by negative 1 to just get y by itself. So here you have negative x plus 3, make sure to distribute that negative 1 to both terms, equals y. And then I'm going to rewrite this as the inverse of f of x equals negative x plus 3. And that should be our answer for part A. For part B, here we'll have y equals 7x plus 8 over 3. We'll swap x and y, so x equals 7y plus 8 over 3. Multiply both sides by 3, and then subtract 8. Then divide both sides by 7. And then I'm going to rewrite it with the proper notation. So here this would be inverse of g equals 3x minus 8 all over 7. And that should be our answer for part B. For part C here, we'll replace p of x with y to start with. And then swap it out. So x equals 2y cubed plus 3. And then solve for y. So I'm going to subtract 3 from both sides. Divide both sides by 2. And now I'm going to take the cube root of both sides to get the cube root. X minus 3 over 2 equals y, and then write it with the proper notation. So p inverse of x equals the cube root of x minus 3 over 2, and that should be our answer for part C. For part D, y equals the cube root, that is a 3 there, of x minus 3, swap x and y, and then solve. So I'm going to add 3 to both sides. And now here, to get y by itself, I'm actually going to cube both sides. So this should be y. And then we'll just leave this as x plus 3 cubed. I know you guys all know how to expand that out with the binomial theorem, but we'll save that for another day. And then write the proper notation. So this should be inverse of h of x equals x plus 3 cubed. And that should be our inverse for D. All right. So you may have to do one of these on your next test. You almost will have to. So just be prepared. It's not going to get any much difficult than these 4, though, so it should be pretty simple. All right, so things to know about inverse functions. If f and g are inverse functions, right? So g is equivalent to f inverse of x, right? That was kind of with that example with the table that I talked about. We also know if xy is a point on the graph of f of x, then on the inverse, y comma x will be a point, right? You just switch the coordinates around. And then with inverse functions, all of the x and the y values are switched, so the graphical behaviors in terms of x and y will also be switched. The key here is knowing the domain of f is going to be the range of the inverse. So let's say we have f of x here, and then we have the inverse of f of x there. The domain is going to become the inverse's range, and the range of the original will become the domain for the inverse because your x and your y values are swapped, right? So just remember the domain and range are switched for the inverses, and then also know 1 and 2 as well. But the domain and range is very important though. All right, so graphically, it's pretty easy. we know that to find an inverse, we simply switch the x and the y coordinates or values. Graphically, this means a function and its inverse will be reflections over the line y equals x because we essentially swap x and y. So example 7, sketch the inverse relation of the given graph. In this class, we're not going to go any much more deeper than finding the inverse of simple straight lines. And so the key is pretty easy. List all the points in to the side of the graph. Find the new coordinates by switching your x and your y, and then plot the new points and sketch the new graph by just kind of connecting the dots. And so let's do that here. Let's take these 4 points and write down the coordinates. So this should be -2, -1. We have -1, 2. We got 2, 1. And then we have 4, 3. There. Now let's find the inverse coordinates by just swapping x and y. So this becomes -1, -2, 2, -1, 1, 2, 3, 4. So now to graph our inverse, first let me just erase those, and I'll graph our inverse with blue here. And so remember, let's graph all 4 of these points. So -1, -2 there, 2, -1, 1, 2, and then 3, 4. And now we can kind of connect it. We went from left to right when we wrote down these points, and so we can kind of do the same thing here. So here you're connecting it to 2, -1, connecting this up there, and then this to that point there. And this would be the inverse, which makes sense, right? If you actually graph the line y equals x, which should be that perfect line there. Wow, that's a really straight line. It is a reflection over that line. So this is correct there. So that is how you graph an inverse function. You will probably need to do this once on your next test. Right, so this is the inverse function. Now let's answer some of the other questions about it. And so is the original relation a function, and why? The original relation is a function, right? If we just take a look at that black, the black passes the vertical line test everywhere. And so this should be yes, it passes the vertical line test. All right, is the inverse relation a function? Now let's take a look at that red graph. Does the red graph pass the vertical line test? And the answer is no. There's a few points where it breaks that vertical line test. So this should say no, it does not pass the vertical line test. All right. Now let's take a look at some of the next two questions here. What is the domain and range of the original function? So remember, domain is going to be your x values, and then range is going to be your y values here. So I'll just write that there. Our domain spans from, for our original function, so I'm looking at the black here, it spans from -2 all the way to 4. So I could just write it like this, or if you wanted to write it like that, that's fine too. Our range is our y values, which spans from -1 to 3. There, or like that. Now, what is the domain and range of the inverse function? So I simply only looked at the black portion of the graph. Now, let me look at the range and domain for the inverse function. So here, I'll do this in blue. And so for the inverse function, the domain spans from -1 all the way to 3. And the range spans from -2 all the way to +4. And so notice how the domain moved to the range and the range moved to the domain for the original function to the inverse function, and that was seen when we graphed it there. Now let's take a look at example 8. The graph of the piecewise linear function f is shown in the figure above. Let g of x be the inverse function of f. Sketch g on the same grid above. And so what we want to do here is the same thing. Pause the video now and try this one on your own. But we want to take note of all the coordinates. So here we have -3, 2. You got -1, 1, 1, -2, and then you got 3, -4, and then to find our inverse coordinates, we're just going to swap x and y. There, -2, 1, -4, 3. What this looks like here is -2 or 2, -3 right here, 1, -1, -2, 1, -4, 3. So this should be our inverse function, and then connect the dots like so. There. And so that's going to be our inverse function, which is a perfect reflection over the line y equals x there. All right? So that is how we would graph that inverse function. So what do inverses do? Well, what inverses do is if you plug a number into the function, it will generally produce a new or different number, right? For example, consider that example that I talked about to remember earlier. That should have been, I think, example 5, the first one with the equations. F of x equals 3x minus 1, and then we got from that example f inverse x equals x plus 1 all over 3. So let's say we plug 2 into the original function, right? We just keep it simple and we find f of 2. This would be 3 times 2 minus 1. That's 6 minus 1. You should get an output of 5, right? Now let's take that output and let's plug it into the inverse function. So now let's find inverse f of 5. This should be 5 plus 1 over 3, which is 6 over 3, which is 2, which was our original number that we started with. And this will be the case with any single number. That's what's kind of cool about these inverse functions, is it essentially will undo a function, right? It's like Command or Control Z. And so if you plug x into a function, right? If we found f of x, we took that value, whatever that is, and plugged it into the inverse function. So we took that whole value and plugged it into the inverse function. You should end up with your original number that you started here with, which is just x. And so that's a key thing about inverse functions. Two functions are inverses only if you plug one into the inverse, or one into the original, right? And then you plug that number into the inverse and you get x. And the same thing if you swap the order of the two functions. So to show that two functions are inverses, we must show that f inverse of f of x and f of f inverse of x both equal x as our output there. And I think this will make a lot more sense with an example. So example number 9, let f and g be the functions below. Determine if they're inverses. So first we want to find f of g of x. So to find that, we're going to plug this whole function of g of x into x in there. So this should be 2 times 1/2 x plus 3 over 2 is going to be like our x here, minus 3. 2 times, and so distribute this and simplify. So 2 times 1/2 x is just x. 2 times 3 over 2 is plus 3. And then we have a minus 3 on the outside. This should just simplify to x. So we got that there. Now let's find g of f of x. And this is kind of the other way around, where I'll use blue here. We're taking this and we're plugging it into x there. So this is 1/2 2x minus 3 plus 3 over 2. Distributing the 1/2 to both terms, you should just get x minus 3 over 2, and then plus a 3 over 2 in the back. These will cancel out, and we should be left with just x on there too. So these two are inverses of each other. Try example 10 on your own, and then I'm about to go over the answer. So show that n and p are inverses by showing n of p of x and p of n of x both equal x as an output. So here, let's find n of p of x, and this is taking this function and plugging it in to x there. So 2 times x over 2 plus 7 minus 14. This would be equal to 2 times x over 2 is just x. Distributing 2 times 7 is obviously plus 14, and then minus 14, this is just equal to x, so that's good there. Now let's take a look at the other way around. So here, let's find p of n of x. I'll use purple here. And so now we're taking n of x and plugging it into x there. So this should be 2x minus 14 over 2 plus 7. This would be equal to 2x over 2 is just x, minus 14 over 2 is just minus 7, and then that plus 7 on the outside. This should be left with x, and so because we have x for both of those, that's showing that they are inverses of each other there. All right, example number 11. The function k is defined on the interval shown above. Let k, or the inverse of k, represent, or k negative 1, right, represent the inverse of k. Find these values here. And so let me show you an easier way than just by graphing the inverse that may save you a little bit of time with these specific questions. So here for A, find k of 6. This is pretty easy, right? When you're just reading, this is just the regular function, no inverses. So when k equals 6, we have an output of 4. So that should be our answer there. The next one here is, let's do C now. Find k of negative 4. This should be when x equals negative 4. This gives us an output of negative 3. So those should be our two answers there. Now we want to find the inverse, right? And so what we did before was we looked for our x values of 6 and our x values of negative 4 and saw where it kind of intersected, or where that point was, and then looked at the y values. However, when we are solving for inverses, what you want to do is you now want to look at your y values and go from y and look for your x's. So for example, find inverse k of 6. Here you're going to look at your y value of 6. That's this point right here, which has an x value of 11. So this should be equal to 11. Right? And this makes sense. If we found k of 11, you would get 6. So then inverse k of 6 should be 11. Let's take a look at D now. Here, find the inverse of negative 4. So we're looking at negative 4 here, and there's no points that intersect it. So this would be does not exist. It's a little tricky. All right, so that would be our 4 answers for example number 11 there. Example number 12, the function g is defined over the interval from negative 3 to 10. So that's g. Let g, negative 1, represent the inverse of g. The values of the table, or of the function h, are given in the table above. Find the select values if possible. And so let's take a look at this. The first one is just a composite function, g of h of 6. H of 6 from the table is just 10. And then g of 10 is looking at 10 as your x, and this should be negative 1 there. So a should be negative 1. The second one, g inverse of h of 0. This is going to be the g inverse of, and then h of 0 is just 3. Now what we want to do here is look, because it's an inverse, we're looking at 3 as our y value. That correlates with this point that has an x value of 4. So 4 should be our answer there. For part C, we want to find g of 8 first. and then find the inverse for the table. So g of 8 is just 0, right? The point 8 comma 0 is on that line, or when you look at 8, it has a y value of 0. Now that we have that, what we want to do is we want to find the inverse of 0. So that is not going to be 3. That's wrong. You want to look for 0 here and look up to find -1 as your answer there too. And then the final thing we have is h inverse of g inverse of -1. So let's find the g inverse of -1. This should be 10 there. So this is going to be the h inverse of 10. And this should be, looking at 10 there, and looking up, this should be 6. So 6 should be 12D there. All right, so that's it for day 1. Here is now day 2, talking about invertibility and preparing for the first FRQ of the AP exam. And so here's the bell ringer for today. Pause the video if you haven't done this yet, because I'm about to go over the answer. So the table here gives values of the increasing function f for selected values of x. What is the inverse of 4? So here all we want to do is, typically you go, if we were, let's say we were looking for f of 4, right? You look for x here and then go to your y. That would be 3. That is not what this is. So do not get confused. Do not put 3 because it is not 3. Instead, what we're doing here is we're looking for 4 in our inverse and going to 6 here. So 6 should be our answer there. Right. Now, for functions, if you have a graph or a table, let's say the function is called f of x just to be easy. For f of x to be a function, remember each input is mapped to exactly one output. Graphically, this can be seen as passing the vertical line test, right? If you have points on a graph here, as long as they pass the vertical line test, they're a function. But as soon as you have 2 points that don't pass the vertical line test, then this is not a function and it breaks the vertical line test. So for example number 13, are the following tables and graphs technically classified as functions or not? And here we're just looking for yes or no. So let's knock out the graphs first. Those are typically the easiest. So A is definitely no. There's tons of rule breakers here that multiple times where it breaks the vertical line test. So this should be no. For D, this actually always will pass the vertical line test. This is a trig function that we'll learn about later, but this is yes, it is, so that's good there. Now let's take a look at the tables, and there's 2 ways to do this. You can either look to see if you have the same x value mapping to different y values, but here all of our x values are different, so it should pass the vertical line test. Also, you could just sketch a quick graph. So -5, -3, -1, 0, 0, -3, 2, 5. It doesn't have to be perfect, but here they all would pass the vertical line test. So this would be yes, it's a function. Now if we take a look at C, right, we see -3, -2, 1, and oh, we see -2 again, right? And we see it twice, and they map to 2 different outputs, so that's no good. If we take a look when we graph it, you may get -3, -3, -2, 0, -2, 5, and that's going to be in the same column, kind of, and then 1, 3. And so here, this would actually break the vertical line test because those 2 would break it, these 2 points right here. So this should be no, it is not a function. All right, so for functions, let's say we have a graph or a table. Let f -1 of x be the inverse of f of x, right? Because of the properties of inverse functions are kind of like switched or flipped, right? Like how the domain is switched and flipped. For the inverse to be a function, each output is mapped from exactly one unique input. What this means graphically is that it will pass not the vertical line test, but the horizontal line test. Let me show you a really easy example, right? let's take a function here, and let's say we just graph a basic semicircle like this, right? This would be considered a function, but then let's say we find the inverse. The inverse should be this semicircle, but flipped like this. That would be what the inverse looks like. The inverse is clearly not a function, right? It does not pass the vertical line test. But let's say I wanted to spare us the trouble of drawing the inverse. How could I tell just from the original that the inverse is not a function? Not a function. Well, it's pretty simple, right? The inverse doesn't pass the horizontal line test, which means when you flip it, right, it's not going to pass the vertical line test. Its inverse will not pass the vertical line test. So if this is our original function here, right, the original is an inverse, but, the original, is a function. But the inverse is not a function, right? So that is very important here. And so if the original is a function and the inverse is a function, so if the inverse is a function, then f of x, the original, right, is considered, and write this down in your notes, 1, 2, 1, right? And that just means it passes the horizontal line test. Right, now let's try example 14. Are the inverses of the following tables and graphs classified as a function? So let's see here. What we want to see is this passes the horizontal line test. So this would be yes, its inverse would be a function. Its inverse is actually just going to be a parabola like that. That's what the inverse should look like. Here, this does not pass the horizontal line test, so no, the inverse of that would not be considered a function. Now let's take a look at B. If we graph B here, you have -5, -3, you have -1, 0, you have 0, -3, then you have 2, 5. Here, they would have 2 points that break the horizontal line test, so no, this would not be considered a function. If you see 2 of the same y values for an original function, you know the inverse is not a function. Right? If we take a look here, if we actually graph this, -3, -3, -2, 0, -2, 5, 1, 3, here all 4 of these points would pass the horizontal line test. So yes, the inverse of this would be considered a function there. So remember, one very common question on the AP test, and one that you'll see on your next test, is I will give you either a chart or I will give you a graph, and I will ask you to determine if the inverse of that chart or that graph is a function. Not if the original chart or graph is a function, because that's pretty easy. It almost will always be a function. I'm asking if the inverse is a function. All right. There's a few ways that I can ask this, and these are all synonymous, meaning they all mean the same thing. The first one is determine if an inverse function of f can be constructed for all values in the domain of f. That's way number 1. Way number 2 is just determine if f is invertible. What invertible means is, can you create an inverse function? Is the inverse a function? And the third one is pretty easy and straightforward. Determine if f has an inverse function. So if you see any of those 3, don't be alarmed. They all mean the same thing. They're asking, is the inverse of this graph a function? This is also a 2-part question. And so this is the only other question that they could ask besides the classic, what type of table is this? Is this a linear, quadratic, exponential table? Give a reason why. This is the other type of question they could ask, which is this function invertible? yes or no. And then part 2 is give a reason for your answer based on 2 things. You need to answer about the definition of what an inverse function means, or what if a function is invertible means. It's going to be the same thing. And then you also need to refer to the specific table or graph. And if the inverse is a function, talk about that inverse graph. What does it look like? If the inverse is not a function, give specific points that break that rule, break the horizontal line test. All right, so we'll work through a few examples here. So let's get into those. So here, if the function is a table, it's pretty easy. Look to see if 2x values give the same y value. So if you have 2 or more y values, then the function is not invertible. So this was a potential question. You could see a table. And then part 1, determine if an inverse function of f can be constructed for all values in the domain of f. Here, all you have to say for part 1 is yes or no. You don't have to say anything else other than that. So here, literally just put no. And the reason why it's no is because we see those two have the same y coordinate, right? If we graphed it, you would see 2, 4, and then 5, 4. And this would not pass the horizontal line test. So no, and then give a reason for your answer. Refer to the points on the graph of f or in the table of f in your reasoning. You can say one of 2 things to talk about the definition. So you need to hit 2 bullet points. You need to talk about the definition, and then you need to give points. And so here you could say the first thing for the definition is the function is not one-to-one. That's a pretty easy phrase to remember, right? It's not one-to-one if it's not invertible. If it is invertible, then it is one-to-one. The second thing you can say is there are output values of f that are not mapped from unique input values. That's pretty long and pretty wordy, so I would stay away from that and instead just say it is not one-to-one. So that would check off point 1. Point 2 would be giving specific points. So here you would want to reference these 2 coordinates of 2, 4 and 5, 4. And so maybe say something along the lines of because f of 2 equals 4 and f of 5 equals 4, the inverse function does not exist. So I think a perfect way to incorporate both of these is my answer for part 2 would literally just be no for part 1 and then say the function is not one-to-one because f of 2 equals 4 and f of 5 equals 4, right? That would be a perfect explanation for that answer. So try example 15. Values of the function f are given in the table above for selected values of x. Determine if the inverse function of f can be constructed for all values. Give a reason for your answer. So here, this should be, if we take a look at the graph, we see 9, 14, 1, and we see 14 again. So we know it's not invertible, right? An inverse function cannot be constructed. So we're going to say no. And then here, I would say it is not 1-to-1 as f of 11 equals 14 and f of 56 equals 14. I think that's a perfect explanation there and gets you both points for that example. All right, now what happens if the function is a graph? It's pretty easy. You would just apply the horizontal line test. You would be given a picture of the graph. You would never have to just work off of an equation alone. And then apply the horizontal, not vertical line test. And if it passes, then it would be considered invertible, or the inverse would be a function. However, when you have to explain why, you're going to want to talk about the definition of if a function is invertible or not, which you're going to want to say it's one-to-one. You do not want to say the horizontal line test does or doesn't work. Saying this actually gets you 0 credit, but you can use it in finding your answer. It's just not an AP way of answering a question. I don't know why they're picky like that, but they are. So you would want to say either one of two things. There are output values of f if it's not invertible that are not mapped from unique input values, or the function is not one-to-one if it is not invertible. Right? So let's say we have this question here. The figure shows the graph of increasing function f on its domain of all real numbers, where x is larger than 2. Determine if f is invertible. This should be yes, right? It does or will always pass the horizontal line test. And then give a reason for your answer based on the definition of a function and the graph of y equals f of x. And so here you want to say something about the actual function itself, and then you want to say something about the definition of invertibility. So here you could say f is one-to-one, and now here's a key thing, right? For a function to pass the horizontal line test, it always needs to be increasing or it always needs to be decreasing, right? There can't be any up or down, because as soon as it goes from increasing to decreasing, boom, it's going to break that horizontal line test. And so you want to talk about the general trends of that function, and it will usually, if it is not invertible, then it will usually say something in here about it. So I would say f is one-to-one and strictly, which means always. So you could use the word always as well. Increasing. And that should be enough to get you credit. Here I said f is strictly increasing, and each output is mapped from a unique input value. That's the other definition for an invertible function. So both of those answers would be full credit on an exam. All right, so now this is a past question and a scoring guide from the AP Pre-Calc exam. The domain of f is given with all real numbers. Don't worry about g here. This question just asks, determine if f has an inverse function. Here you can see 2 points that break the rule, right? So f of 1 equals 1 and f of 5 equals 1. But then we also see this here, right? F of 2 equals 3 and f of 4 equals 3. So it's like double bad. For part 1, all you would have to say is just no. That's fine. And then for part 2, give a reason for your answer. Here you would want to say there are output values that are not mapped from unique input values, or you can say the function f is not one-to-one. And then you would want to give those specific points, which says because f of -1 equals 1 and f of 5 equals 1, you could have swapped those out with those 2 points. That would have been okay. The inverse function does not exist, something along those lines. But notice here it says a reason that only states it fails the horizontal line test is not sufficient enough to get credit. So this is one question where AP is a little picky at times, but rightfully so. And so just make sure that you have the correct wording for this type of question. All right, so FRQ number 1. On the AP exam, you will have a 6-part FRQ that will either give you a table or a graph. This will be f of x always, and then you'll have g of x, which will just be an equation, and you will have to answer 6 questions about it. We've already done a lot of these questions, so I'm just going to give you one example for each of these, and then let you try some on your own. There'll be one of these on your next exam, one of these 6-part questions on your semester summative. And so the wording will be the same. It'll just be different numbers, tables, graphs, equations. With all of these questions, you should have access to Desmos, so feel free to use it on your homework. Be prepared for one of these on your next test, semester summative, and one will definitely show up on your AP exam as well. So question 1, composite functions. Find the value of h of 4 as a decimal approximation. So here you want to also show your work. So the way I would show my work is I would say h of 4 is g of f of 4. this is going to be equal to g, and then f of 4 is 2. And then here, you could just plug this directly into your calculator. So 3 log 2, 3 times log base 5 of 2. And then here you want to use Desmos, and you want to go to functions, and then look for that custom log. So I will show you how to do that in class. And so once we have that, you should then get your answer of 1.292. And remember, it wants it as a decimal approximation, which means 3 decimal places. I will give you no credit if you give me fewer than 3 decimal places there. Unless it is like just a number like 4 or like 6.5, then you don't need to add extra decimal places. All right, number 2, inverse functions. You may be asked to find the y values or the x values when the y value equals a certain number, or be asked to find an inverse of a function. Both will require you to look at your y values and then find your x value. If you're using a graph, it typically will be a nice clean integer. So let's work through these examples. Find where g of x equals 3. That on the graph is going to be that point, which is x equals 2. Find all real zeros. That would be when x equals -1 from the graph. Find the inverse of 2. And so here you want to look here at this inverse. This should be this point right here, which is x equals 3. Or the way I would write this would be of inverse 2 equals 3. And then find the inverse of -1. This has an x coordinate of 0. So I would say g inverse -1 equals 0. That's how I would answer those questions there. Right, the next one is the domain consists of 5 real numbers. Find all values for which f of x equals 4, and then find the inverse of 6 or indicate it is not defined. So here there's 2 values of x for which where f of x equals 4. It's going to be 2 and 5. So I would say x equals 2 and x equals 5. And then here, find the inverse of 6. You're looking at 6 here. And so this should be the inverse of 6 equals 1. And that would be my answers for those 2 there. Right? Let's move on. So the third type of question you could see is using your graphing calculator to find zeros or intersection points. So try to find this now. Here you're going to graph 2 equations. You're going to graph y equals 0.35 x cubed minus 3.5 x squared plus 11 in Desmos. So remember, this you have Desmos, so pull out Desmos right now. And then you're going to graph the line, another line, y equals 5, and then find your intersection point. You may have multiple. In this case, you should have 3. And so here it should be x equals -1.235. And so we want decimal approximations. 1.413 and 9.822 should be our 3 values of x there. The fourth one is end behavior. Just remember limit notation. So it's going to be the limit as x approaches either a number or it's going to be positive or negative infinity. One of those. Your function, which this is typically going to be g of x for this problem, equals, and then what your limit is equal to. It needs to be in this form. If it is not, it will not be given credit. So here you could use 2 things. One, I would always say check your work with Desmos, right? You can plug this equation into Desmos and look at the end behavior if you're ever not sure. But feel free to make things a little bit easier by using Precalc as well. So here, the function g is given by this polynomial function. Find the end behavior as x increases. This should be the limit as x approaches infinity. So only have one limit statement of g of x equals, and remember, as x increases is positive infinity, as x decreases is negative infinity. And now, because this is a positive leading coefficient and an odd degree, this is going to behave like y equals x. So as x goes to the right forever, this is going up to positive infinity there. Now for a rational function, remember the rules. If you need help with this, for polynomial functions, visit lesson 1.6. For rational functions, 1.7. For exponential functions, 2.3 would be the 3 lessons you would want to hit on. So here, this is take your leading terms, x squared over x. This is top heavy, so it should just simplify into x, and then that equation will be your end behavior. So the limit as x approaches negative infinity of g of x equals negative infinity there, and that should be our answer. And now for an exponential function, g is given by that exponential function. Determine the end behavior as x increases. This should be the limit as x approaches infinity of g of x. And now to determine what this is, our a value is positive, but our b value is less than 1. So this is going to be an example of exponential decay. So we should have something like this, which means as we increase, this is going to tend towards 0. So that should be our limit statement for example 26. Finally, example 5, determine the type of function from a table. Example 27. This is the question that you've had lots of practice with. Determine if it's linear, quadratic, or exponential. Here, if we take a look, we are minusing 1, plus 1, plus 3, plus 5, and then this should be plus 2, plus 2, plus 2. So this should be a quadratic. And then remember the wording here. You want to start with over, equally spaced, inputs, the outputs have a second difference because it's quadratic and then in this case, our second difference is plus 2. So that would be perfect. You have all 3 things that I'm looking for there. And then number 6, this is some more practice with this question. Determine the invertibility of a function. This was actually the question from 2 years ago, the free response question. So determine if f has an inverse function. Here clearly does not pass the horizontal line test, so I'm going to say no. Give a reason for your answer based on the definition of a function. Refer to points. So here you only have to reference 2 points. So we could say 0, 1 and 3, 1. There's also negative 3, 1. So either one of those, as long as you have 2 of those, that works. You could have 2 of other points too, but I like to choose integer coordinates because it's nice and easy. So I would say no, and then I would say f of x is not 1 to 1 because f of 0 equals 1 and f of 3 equals 1. So that would be my answer there. Example 29. The function f is defined for negative 2 to 4. Determine if f is invertible or not. So here it clearly breaks the horizontal line test, so it is not invertible. So I'm going to say no. And then it is not 1 to 1 because, and then I want to find 2 nice integer coordinates. So right there and right there, negative 1, 2, and then 3, 2. So I could say because f of negative 1 equals 2 and f of 3 equals 2. And that would be enough there. And then one more example to wrap it all off. Determine if the table is invertible or not, or if an inverse function of f can be constructed for all values in the domain. Here we see you got the coordinates 2, 2, and 5 comma 2. So this would be no. And then I would say f, where f of x is not 1 to 1, because f of 2 equals 2 and f of 5 equals 2. And that would be my answer there. If you have any other questions, please come see me in office hours and I'll be willing to help. I'll talk to you guys later. See ya.